Okay, our last speaker for the event is one of Dr. Kate Sparante's students, Mr. Daniel Ross. We'll be talking about the future benefits of quantum computing. Everyone else is doing it, so I guess I'll do it. Good afternoon. First, I want to thank you all for granting me this opportunity to present. I have something to present to you that I think is truly magnificent. It's quantum computing. It holds a very bright future, and it's completely unlike any other kind of computing. So here's a little overview. I'm going to explain a little bit about what quantum computing is. Then I'm going to give you a brief history of quantum computing and some of the people, the pioneers of it and whatnot. I'm going to explain how quantum computers work a little more in depth, give you a little bit of the physics behind it. And then I'm going to tell you the advantages of quantum computing versus conventional computing, as well as some of the limitations of quantum computing that probably will never be able to replace conventional computing. I'm going to go over the current difficulties of quantum computing and future applications of quantum computers, the practical stuff we can do with it and how it can benefit us. Alright, so what is a quantum computer? It's hard to explain, but I'll do my best. A quantum computer is a computer that processes information using quantum particles. Conventional computers use a whole bunch of transistors, usually millions or billions now, and diodes. So it's made out of atoms, obviously. This is just made out of generally an electron. So conventional computers process their information with a binary code. Ones and zeros making up the bits. But a quantum computer, since it's quantum, you can use the rules of quantum physics, like superposition, so it can simultaneously be 1 and 0. Thus, if it's making a calculation, it can instantly find the answer because it already has both variables. So here's a brief history of quantum computing. Back in the 70s, theories began to arise. They were extremely abstract. It was more of just scientists discovering new things about quantum physics and wondering if they could create quantum information systems or ways to store information on quantum particles. In 1985, David Duchesne, that's probably not right, but published a paper that suggested the possibility of building a computer that uses quantum gates in place of the regular logic gates that they were using in processors. In 1995, Peter Shor, he was working for AT&T, I believe. He discovered a quantum algorithm. It's now known as Shor's algorithm, and it hasn't been successfully used yet because it needs a quantum computer to be able to work, to be run on. But it would basically be able to get through any type of cryptography. It could break any code. And I know that sounds really bad, like someone's just going to steal your bank account, but the good thing about it is that it creates new cryptography also. Stuff that would be virtually impossible to break unless you have a quantum computer. And you have to be like a millionaire. 1998. First experimental demonstration of a working 2-qubit NMR, nuclear magnetic resonance quantum computer, went down. It happened at Oxford University. Jonathan A. Jones and Michelle Mosca. It didn't do anything too spectacular, but just the fact that it was running off of quantum particles was cool. 2011, the company D-Wave created their first commercially available quantum computer. It's 128 qubits, I believe. I'll explain qubits in a second. But around 2013, 2014, Google actually bought a quantum computer from D-Wave Systems. It's called the D-Wave System 2, and they partnered with NASA to buy it, so it's actually a real thing that's going on now. So how does it all work? It's really easy to explain. No, it's, quantum computers process information using subatomic particles. They're called qubits, like bits in a normal computer, but they're quantum, so they call them qubits. Unlike conventional computers, they process information conventional computers process their information just with transistors, as I mentioned before. But quantum computers are not so limited. Quantum computers use the subatomic particles in quantum superposition, enabling them to be both a 1 and a 0 simultaneously. I would try to explain quantum superposition, but I'll probably just butcher it so much because I don't go to Harvard University. So quantum, explain some of the advantages of quantum computing. Quantum superposition enables quantum computers to consider and manipulate all combinations of bits simultaneously. One interesting thing they do, since everything wants to be as stable as possible or in its lowest energy level, is they can optimize it very well, and they can tell you how they got this answer and what was the lowest energy state to get to that answer. So it's really good when there's two variables for optimization type problems. Yeah, this is extremely useful for optimization problems. So, huge advantages, more secure data encryption will be available. For military and stuff like that, that's tremendous. They are investing quite a bit of money into quantum computing now. Probably want to get there before the Russians. So the difficulties of quantum computing. It's not so easy after all. Subatomic particles are extremely difficult to trap. You have to trap one electron with, I think they said it's about 8 atoms, that the trap's made out of 8 atoms. Just to engineer that is insane. And when you're building up a system of qubits, if one doesn't get in there correctly, then they just have to restart it, and that's expensive. Yes. So presently, the difficulty for building a quantum computer is due to the particle's instability, and by that, they just move around too fast. They're too sporadic. Particles in superposition are extremely unstable, and they quickly choose a fixed quantum state. This is known as decoherence. Basically, superposition isn't preferred by subatomic particles. They want to get their lowest energy state, and they just want to be left alone. But we are trying to figure out ways to error correct them, because if it does just choose a side, it chooses an energy state, then you're going to get skewed results, and it's useless. So some of the future applications, I'd say the best application, the most beneficial for the humankind is probably medical. It could be very, very successful in medicine with, that has to do with genetic coding. Say there's a really good drug that's out that cures, I don't know, HIV, but for some people it has some genetic side effect and it turns the lights off. They can't give that to the public because they don't know who's going to have the side effect and who's not. But with a quantum computer, they could actually run your genetic information and find out if you are one that can receive that medication. Also, again, with chemistry, everything wants to be in its lowest energy state, and that's exactly what this optimizes. So it can process thousands and thousands of chemical reactions at the same time, which would take a normal computer, a month, maybe 2 months, I don't really know. Engineering is another big field. Optimization, again, civil engineering, they always have problems with water, getting it to different cities, and it always gets messed up, and it's not good. And it's just because they simply can't optimize what every consequence is going to be. The third application is weather forecasting. Now, computers that are presently available, they do a decent job at weather forecasting, like the day after the storm happened. They're just too slow. We need something faster. This could avoid hurricanes, tornadoes, or well, not avoid them, but help people evacuate sooner, save lives. And last but not least, space exploration. Bianca just talked about space. I like space. No, space is vast. There's so much that needs to be found out, and not enough computing power. It would take a lifetime with computers now, to figure out just what another galaxy is made out of. All right, so in conclusion, went over what a quantum computer is, then went over a little history of the theories that helped create quantum computing, went a little more in depth on how quantum computers work, went over some difficulties with it, and I went over how they're better than conventional computers, and some practical applications. Is there any questions? You, sir.
Are these inherently low temperature devices, or do they run at room temperature?
They do. That's a really good question. Since the particles are so unstable, they're moving around so fast, the only way to actually use an operating quantum computer is to cool it to near absolute zero, so 0 degrees Kelvin. I think it's 0.001 degrees Kelvin or something. That's the most expensive part of running one, actually. Yeah. Yeah.
A very tiny block. The particles that are unstable, is there research? Are we close to?
Well, yeah, we have working quantum computers. Most of them are a D-Wave system. It's controversial right now if it's actually a quantum computer, if it's running some other way. So D-Wave just says we don't really care what it is. It does these problems that we want it to do. There's other types. So there's quantum annealing. Then another type is just quantum gate computing, which is more like the architecture you find in an Intel processor or ARM processor. I got way too technical, probably, just again, but...
Can I invest in D-Wave systems?
Yeah, you can. The thing is, though, Google bought one, and now Google's trying to make their own quantum computer without D-Wave. So I think Google's... Google, really hasn't found that much use for it either as NASA. It did do some optimization problems faster than a conventional computer, but as far as the speed test, it wasn't that fast for a lot of things.
How big are they?
It's as big as a Land Rover, probably. And the actual CPU is smaller than the head of this microphone, but it's all for cooling pretty much. It's cooled with nitrogen. I think that was the 3 questions, so. One more, encore.
Okay, so I've heard that we as humans, we only see life around us as we define it as code. So do you think by having a quantum computer can help us understand life around us?
Yeah, absolutely. It's interesting because a lot of things are happening that are actually superposition events that aren't on the quantum level, like noise canceling headphones. You have an annoying baby in an airplane, you don't want to hear it. So your headphones turn on and record that sound and play the complete opposite and make destructive waves. So the sound exists and the sound also doesn't exist at the same time, simultaneously. So I mean, I think it would help us figure out other things, like probably with light and stuff like that, that's impossible for us so far. Thank you.